Hello everyone, welcome back to my channel. So in this video we are going to learn about Maxwell's second equation for electrostatics. So Maxwell's second equation for electrostatics, and also we are going to see the relationship between E bar and V. So we'll discuss both these topics, right? If you are first time to my channel, please consider subscribing and don't forget to hit the bell icon so that you will get the notifications from my channel. So when I do the videos like this, you'll get some notification. Right, so Maxwell's second equation for electrostatics. So it is again derived from potential only. So VAB is equal to minus integral A to B E bar dot DL bar. Suppose if the line, if the contour, so where you are going to bring, right, so where you are going to move the point from A to B is a closed integral. So consider the closed contour here. For Maxwell's second equation, you have to consider closed contour. It is closed integral, closed line integral, right? So VAB is this. So what is VBA? So VBA is equal to minus integral B to A E bar dot DL bar. So what can we write here? So VAB, since only limits are reversed here, so limits are reversed, so we can write minus VBA. Yes or no? So minus VBA, if you take a negative sign here, we can reverse the limits. So that it will be equal. So VAB is equal to minus VBA. So what will be VAB plus VBA? VAB plus VBA is equal to 0. So VAB plus VBA is equal to 0. So when VAB plus VBA is equal to 0, what can we write? Integral some differential length L E bar dot DL bar is equal to 0. Let it be from B to A or anything. So closed integral E bar dot DL bar is equal to 0. So this equation is called Maxwell's second equation. This equation is called Maxwell's second equation for electrostatics in integral form. So let me explain more clearly like this. If there is a closed integral like this, so closed contour like this, so suppose this is the starting point here. So here you are moving the charge in this direction. So this is the path where you are moving the charge here. So again end point will also be same, right? So for closed path, end point is equal to the starting point, that is VB is equal to VA. In that case, when VB is equal to VA, in that case, so what will be VAB? So VAB, just now we have seen it is equal to VB minus VA, but VB is also equal to VA, so VAB is equal to 0. VAB is equal to 0. When VAB is equal to 0, when this is equal to 0, what will happen? Closed integral E bar dot DL bar is also equal to 0. So A to B, instead of writing A to B, we are writing that closed integral here L, because A is equal to B. In this case A is equal to B, so integral L E bar dot DL bar is equal to 0. Okay, so I hope you have understood very clearly what I have written earlier. Right, so this is called as Maxwell's second equation for electrostatics. So what does it represent? So if you write in theoretical form, so thus to move a point charge, okay, so thus to move a point charge in the presence of electric field, in the presence of electric field, okay, in a closed path. This is very, very important. If you don't have closed path, you will get some potential value, but when the closed path is there, so potential value is always equal to, potential value is always equal to 0. When potential is equal to 0, so the E bar dot dl bar is equal to 0 in a closed path. Right, so thus to move a point charge in the presence of electric field in a closed path, comma, work done is 0. Work done is 0. Okay, so when VAB is equal to 0, what is work done? So work done is equal to VAB by Q, or VAB, sorry, reverse, no. So VAB is equal to W by Q, right? So when VAB is equal to 0, W is also equal to 0. So work done is 0. Okay, so work done is thus to move a point charge in the presence of electric field in a closed path, work done is 0, because you are not moving anything, right? So even if you move also, it is again coming back to the same point, right? So it is again coming to the same point because it is a closed path. So because end point is equal to the initial point, so that work done is 0. There is no work done because you are not moving it. Finally, even though you are doing some work, but you are not moving the point to other places, or initial and final point is same, so that is why work done is 0. The net work done is 0. Okay, so this is Maxwell's second equation. So if you apply Stokes theorem, which converts closed line integral, okay, so applying Stokes theorem, so Stokes theorem, what does it do? So it converts closed line integral into surface integral. Okay, E bar dot dl bar is equal to integral S del cross E dot ds bar. Okay, so E bar dot dl bar is equal to 0, so this is also equal to 0. When this is equal to 0, so what can we write? Del cross E bar is equal to 0. So this is called as Maxwell's second equation for electrostatics. Okay, so for electrostatics in differential form. Okay, so this is Maxwell's second equation for electrostatics in integral form. This is the Maxwell second equation for electrostatics in differential form, so which is again come from the same concept of potential. Okay, so when closed contour is there, when closed path is there, so net work done is equal to 0. So based on that, Maxwell's second equation of electrostatics has been developed. Okay, so next is the relationship between E bar and V, that is electric field intensity and electric potential. Okay, so one relationship we have already seen. So V is equal to integral L E bar dot dl bar. Okay, so V is equal to this, we have already seen, that is VAB we have seen, of course, minus integral A to B E bar dot dl bar. This we have already seen in my previous video, right? So now reverse conversion, what is E is equal to E bar, or E bar is equal to what? In terms of V we have to find. Okay, so V is equal to integral L this E bar dot dl bar. So what can we write? dv. So dv is equal to minus E bar dot dl bar. Okay, so dv by suppose dv bar is equal to, so if you have E bar, right? So if you have, let us take, let E bar is equal to Ex Ax cap, Ey Ay cap plus Ez Az cap. Okay, so generally we'll have electric field in this format only. We have x component, y component and z component if you take a Cartesian coordinate system. Okay, so and if you take a Cartesian coordinate system, what will be dl bar? Dl bar is equal to, so dx Ax cap. So this already I have explained you how to take differential length in my basic videos. So basics of EMTL videos I have already explained you. If you have not seen that videos, so I'll give the playlist link in the description. From there go to the basic videos, right? See there, you'll understand how to write the differential length formula. Okay, so dx Ax cap plus dy Ay cap plus dz Az cap. Okay, so this is the formula for differential length. So then what will be dv? dv is equal to minus, okay, so minus Ex Ax cap in the place of E bar here, right? In the dv I am writing here dv as it is I have written. So in the place of E bar I am writing this. Okay, Ex Ax cap plus Ey Ay cap plus Ez Az cap dot dl. dl is dx Ax cap plus dy Ay cap plus dz Az cap. Okay, so we know that Ax cap dot Ax cap is 1 and remaining Ax cap dot Ay cap is 0 and Ax cap dot Az cap is also equal to 0. Similarly we can apply it for, so if we have same vectors, same unit vectors, it's the dot product between them is 1. If you have different unit vectors, dot product is 0. So what does it become now? So Ex Ax cap dx Ax cap, so it will be minus Ex dx. Ax cap here, Ay cap here, so it will be 0. Next Ex Ax cap dz Az cap, Ax dot Az is equal to 0 again. Similarly Ay Ax, so Ay Ax is also 0. Ey Ay dot dy Ay, so it will be minus Ey dy. Similarly it will be minus Ez dz. So this is dv. Okay, so from total probability, okay, total integral concept. So how can you write dv? So dv is equal to dou v by dou x into dx. Okay, plus dou v by dou y into dy plus dou v by dou z into dz. Okay, this is from total integral concept, right? So let this be equation number 1 and let this be equation number 2. So from 1 and 2, if you compare 1 and 2, both left hand sides are same, dv, and here also dv. So minus Ex, in the place of minus Ex we have dv, dou v by dou x. So minus Ex is dou v by dou x. Similarly minus Ey is dou v by dou y. Similarly minus Ez is dou v by dou z. Okay, so these are the relationships between the components. Okay, so if you have a components like this, so vector is a scalar quantity, right? So potential is a scalar quantity. So Ex component, if you want Ex component, if you are given with a potential, suppose if you are given with some v is equal to 2x square yz like this, okay, and you are asked to find E bar, and you are asked to find E bar. So how you are going to find? Using these formulae only. So what will be E bar? Actually, what will be E bar? E bar is equal to EX AX cap. So we need to find EX, right? So what is EX? EX is minus dou V by dou X. So differentiate this with respect to X. So it will be minus 4xyz. So x square differentiation is 2x. So 2 into 2 is 4, and minus signal is there. So minus symbol is there. So it will be this. So that will be EX. Similarly, find EY and EZ too. So you can write E bar like this, right? So I'm just telling you the simple application. So if you are given with potential, you can find the E bar like this. Understood? Right. So what will be E bar here? So E bar is equal to EX AX cap plus EY AY cap plus EZ AZ cap. Okay. So what is EX here? EX is minus dou V by dou X. So minus I am taking common, dou V by dou X into AX cap, because EX is equal to minus dou V by dou X. So minus already I have taken common, so this will be dou V by dou Y into AY cap plus dou V by dou Z into AZ cap. So what is this? Dou V by dou X into AX cap plus dou V by dou Y into AY cap plus dou V by dou Z into AZ cap. Gradient. Okay, gradient of V. So E bar is equal to minus del V, minus del V. Okay, so del V formula already I have told you how to write the formula for del V, where V is a scalar here. So V is a scalar quantity. Always we know that potential is a scalar quantity. When the input is a scalar quantity, then output will be a vector quantity in the gradient expression, gradient equation. Okay, so E bar is equal to minus gradient of V, minus gradient of V. So this is the relationship between E bar and V. Okay, so this is one relationship, right, in vector in integral form, and this is another relationship in differential form. Okay, so using these two forms we can find potential if you are given with electric field intensity, or you can find electric field intensity if you are given with potential. Okay.